So now, last but not the least, from Professor David Wright, Tidewater Community College, he's going to be telling us about the WISE strategy for problem solving. Thank you so much, David. Please take it away.
Okay, thanks very much. Here's my picture here in a second. There we go. Great to be here. I love this Chesapeake section. What a great turnout we have this time. Now, I'm going to give you a disclaimer here in the beginning. My PowerPoint presentation has much more than I'm going to talk about. A lot of examples we won't go into. We will post it on the website afterwards, though. So don't fear, you'll be able to see it all. So don't worry about taking notes, and then details will show up later. All right, let's begin by sharing my PowerPoint here. All right, it's about the WISE strategy for problem solving. I'm an emeritus faculty, it means I'm retired, but I still keep a connection to the college. I love working with the faculty and in the planetarium, so it's great to work at a community college. I love it. All right, my proposal is going to be this. Physics students benefit from a structured problem solving strategy. I'm going to present the one that I use, which is based upon my research, but I would say pick one you like that fits your style and teach it to your students, practice it with them, and I'll show you what I did. I believe it increases accuracy, it promotes organization, and it improves communication. Well, let's see how it does that in just a minute. All right, so this whole thing started, as I can tell, about 1948 with George Polya's How to Solve It, which it gave a 4-step approach. And there's been many, many others. I could go on and on. I did that in my research. So I developed a strategy on the process of researching and writing my PhD dissertation at Virginia Tech. Go Hokies! I found that after a problem-solving strategy, such as the WISE strategy, I never want to go about without teaching it without it. Now, I do a lot of demonstrations, teach the theory as well. When it comes to problem solving, I love using the problem-solving strategy. Here's what mine looked like. The W is what's happening. What's the physical principle? Is it a kinematics problem? Is it a dynamics problem? Is it a work energy problem? Is it an electrical potential problem? And once you've decided that, you'll know what kind of diagram to draw. I'll give you a lot of examples of this in a minute. And oftentimes include a sketch as well as a diagram. Of course, a diagram depends upon the type of problem. Is it a force diagram? Is it a velocity diagram? What does it happen to be? You want to list the knowns and the unknowns. And this is really critical. And those knowns and unknowns are based upon that diagram you've just drawn and the information in the problem itself. Now, once you've done that, you've decided what type of problem it is, what's the physical principle, drawn your diagram, listed your knowns and your unknowns, may divide it into 2 pieces, for example. Once you've done that, that's half the battle. That's half the battle. Then you can go forth and solve the problem. You've got yourself all squared away, ready to roll. So after you've got all this discovered, then you're going to isolate the unknown, find an equation or equations that fit the information you've got and what you're trying to find. You're going to solve them symbolically. Never plug a number in, or almost never, until the very end of the problem. This keeps you straight with the physics. Then you're going to substitute both the numbers and the units into the equation, and then you're going to check the units. Then finally, you'll evaluate. For example, is the sign correct? Does it match the diagram you drew, for example? Is the magnitude reasonable? Students don't look at the number. Oh, I got 58. Good. Check the back of the book, perhaps. But I had a student once that said the orbital velocity of the satellite was 5 microseconds. Didn't bother them at all. They never bothered to look at the answer and think whether it was reasonable or not. And are the units correct? This is well beyond the blind faith technique. The students use the blind faith technique, which means I'm solving for velocity. Therefore, I know the velocity must be in meters per second. So I'll write down meters per second at the end of the problem, right? That's what they like to do. Not so much. Okay. Have them use a template like this. Template's not required, but it helps to keep them organized. The sketch here and the diagram up top, along with the knowns and the unknowns. The symbolic solution showing up here under isolate the unknown. The substitution of the numbers and the units. A units check. I'll show you how that works in just a minute. And finally, evaluating the sign, the magnitude, and the units. This is what the template looks like. Here's an example. The ball is run up a 10-meter high cliff with a velocity of 20 meters per second and an upward angle of 30 degrees. How long before it hits the ground, and what is the velocity just before impact? So here's my sketch up here. And as you can see, it shows what's really actually happening in the problem. But the students have been taught that if the acceleration is constant, all you really have to know in a kinematics problem is what's the beginning of the problem, what's the end of the problem. And so my diagram shows that. Here's the beginning of the problem. Here's the end of the problem over here. This is my displacement vector, my final velocity vector based upon the setup of the problem, my initial velocity, the acceleration, of course, which is always down in a free fall problem, and the y vector, the y component of the displacement vector is pointing down. So when you're looking at that diagram, it's easy to get the signs correct over here. Y is going to be negative. V naught is V naught x is going to be V naught times the sine of the angle, and so forth. Acceleration is going to be negative as well. I might note that I always, in these problems on my homework and the test, I don't worry about significant digits. I say just choose 3 significant digits in your answer and keep that consistent. In lab, of course, we take advantage of significant digits. My theory is that in problem solving in an algebra and trig-based physics class, they've got enough to worry about just to get the problem solved. Having to add in this added problem of keeping significant digits correct is just over the top in my book. Anyway, you may disagree, and that's fine. Here's what you do. You find the equation. Of course, though, there's 2 ways we can solve this problem. We could, solving for Vy and solving for T, you can solve them independent of each other. I chose to solve for Vy first because it didn't require the use of the quadratic equation. Students hate the quadratic equation. You could just as easily have found the time first and then found the velocity. But if you find the velocity first and then the time, you can avoid the quadratic. These students love to do that. And the idea being, there's a plus or minus here, but the plus or minus comes from the diagram. They can tell that the Vy has to be negative because it's in the downward direction. Substitute both the numbers and the units into the equation. You can see here, and then they do a check. Meters per second squared, meters squared per second squared plus meters squared per second squared. Take the square root, you get meters per second, and that's great. And the negative sign is picked because it's from the diagram that I drew. And we find the velocity, the inverse tangent to find the angle, and there we have our, and we check our units on the time. We plug that in as well. We check the units, they match like they're supposed to be. The sign matches the diagram, and the magnitude is fairly reasonable. It didn't take 9 minutes, for example, for things to be tossed off the cliff, or 25 microseconds. The magnitude seems to be somewhat reasonable. Here's the whole thing put together on the template. Here's my diagram, my list of all my knowns and unknowns. See what I'm trying to find. Now I can do my symbolic solutions here. This is a sketch of how to take care of the final velocity, which of course is the Pythagorean theorem to find the final velocity. And we substitute both the numbers and the units. Now, because the knowns and unknowns are right up here where they're easy to see, they can just check back. Oh, there's what my, my y is minus 10. Okay, y is minus 10. I put it in there. Often is that their papers are so disorganized they can't find anything. I think it was 10, maybe it was 10. This keeps them organized. So here's my take on this. It improves accuracy. It slows them down. That's one important thing in solving physics. You want to do it quick. Find the equation, plug the numbers in, and boom, be done. It slows them down. This is important. I just studied with my dissertation. I studied 1,337 mistakes. I categorize them between conceptual mistakes, algebra and trig mistakes, or careless mistakes. I found that 46%, in my estimation, were simply carelessness, miscopying, using the wrong units, sign errors, arithmetic errors, overlooking information, answering the wrong question, leaving out variables, drawing sloppy diagrams, and so forth. And writing down every step avoids mistakes of just doing things in your head. So proper diagrams can help with the signs. Units catch algebra mistakes. Listing the knowns and the unknowns in one place is helpful in finding, clarifying the variables. And if symbolic solutions are not done, the number is simply plugged in too early, it's very easy to make a mistake that can easily be found. That cannot easily be found. You just have a whole series of numbers. Teacher can't find it either. So also the physics of the problem is not lost in a flurry of numbers. Promotes organization. They get a starting point, a series of questions to ask. They don't panic in the beginning of the problem. It provides them the consistent structure. It can be used for all their problems. We'll talk about the formula fact sheet later. It improves communication. It's easy for you as a professor to help them through the problem because you can see exactly where they're headed. If the diagram is wrong, it's pretty obvious. If following the symbolic solution keeps the physics intact, and students can help each other. They see what's happening. It's easier to find out where the mistakes are and to talk to each other. I don't like the way you picked that solution. Why'd you pick that particular equation? And it's based upon your diagram and your knowns and your unknowns, the principle that's involved. So it keeps them all able to talk to each other. Here's an example of a problem that comes in 2 steps. I'll publish this so you can see it later. Of course, what ties these things together is the velocity at the end of part 1 is equal to the velocity at the beginning of part 2. So I've got 2 sets of knowns and unknowns, and I can decide which one to start with. I'm going to start with number 1 because 1 only has 1 unknown, and the second part has 2 unknowns. So the first part was produce an unknown that can be used in the second part. So it helps them plot their strategy. Solve it symbolically again, substitute the numbers in the equation, and off we go. Here's a dynamics problem. Here's a work and energy problem. Now the formula fact sheet. This is where they kind of organize their thinking about that particular equation. So we're going to use this kinematics formula fact sheet to give you an example of what I'm talking about. Here's a typical diagram they might draw, typical sketch, how you draw a 2-step problem with a kinematics problem. Knowing that it requires both a beginning and an end, you have to identify the beginning and identify the end, all the units that need to be used. And for example, what might you list on a formula fact sheet? You might list, for example, when you list your knowns and unknowns, you will usually find you have 3 knowns and 1 unknown. Every kinematics equation has 4 variables. Pick the one that only has 1 unknown. Seems obvious to us as teachers, right? You'll often get the signs for the knowns and unknowns from your diagram. So check the diagram carefully. The direction of the acceleration is always the same as the direction of the force that causes it. And if the acceleration changes in a problem, you have to split the problem into pieces. These are some of the things you might want to help your students kind of categorize. What things do they have to look for in an equation when they're solving them? Here's some formula fact sheets now for dynamics, for buoyancy, and for electric fields and so forth. Now, what were the student comments? I feel more confident than 10 weeks ago. I have learned to go slow and think. I feel better to organize myself and define the problem, which in turn makes it easier to choose the proper equation. It makes problem solving standardized, which makes the info of the problem easier to communicate to others. And then one student said, solving symbolically makes it easier. I used to think it was easier to put numbers in at first. I've changed my mind. The strategy was optional in the beginning. I would have done it my own way. I wouldn't have learned that. You would have chaos, let them do what they wanted. One student said, that was kind of an interesting way to put it. Reduced my errors greatly. Strategy made me be very careful in my work. And one student had physics before said, in another institution, said it was like big numbers chopping me up. My first time through, I got the impression that these are the equations, these are the numbers, do it. Don't try to understand. Wow. All right, final notes. If you don't require the strategy, diagrams, lists of knowns and unknowns, and then grade the students accordingly, they won't do it. Their response, why do you care? I work the problem as long as I get the answer. You say, you don't get it. The answer is not what we're shooting for. It's the strategy, the logic, the organization to be able to tackle problems and be able to solve. That's what's more important. The process is much more important than the product. You need to practice the components explicitly. Teach them how to draw diagrams. Help them through their solving of symbolic solutions. If they can solve if they can draw a proper diagram, and if they can solve it symbolically, that's half the problem. Just drawing the diagram and listing the knowns and unknowns is half the problem of the battle you're going to fight. Develop the formula fact sheet as a group. This helps them to identify when and how to use equations. And I talked about significant digits before. So conclusions. Of 136 students, 100 said the Y strategy was very helpful, 34 said it was somewhat helpful, and 2 said it was not helpful. And I didn't identify these with particular students. They weren't just polishing the apple here. It was hopefully honest conclusions. 126 said that we continue to use the strategy even if it weren't required. It made my heart feel good. My class retention rate went from 70% to 86%. That's 70% over 10 quarters. In the 3 quarters, it was like 85, 86, and 87. Dramatic increase in my results, at least anyway. My other conclusions are keep it simple. I started out with a multi-step strategy, many more than 4 steps. And the students didn't like it. They hated it. They got very frustrated. They were just tied up in knots. So keeping the strategy simple is important, and modeling it yourself and asking them to model it. If you expect the why strategy, it must be required. Many students come in, if they were not required to use it, they would not have used it. They may do it without a template, but all the components of the plan must be in there. I feel like I just run a race. Anyway, I really sincerely believe in the process of using a strategy. You don't have to use mine, although mine was based upon a number of giants whose shoulders I stood upon, as Newton said. But a strategy helps you teach, helps the students follow what you're doing, helps you communicate with them, slows them down, which they'll complain about it first, and helps them to really get a handle on how they go about tackling and developing your own personal strategy. All right, any questions? I guess we don't probably have time for that.
Thank you, David. Yeah, go ahead. Go ahead,
No, go ahead. No, go ahead. Go first. I heard your voice. Go ahead.
I know they won't all love physics.
Go ahead.
No. I was just going to. I mean, we're I think going to be having a break and a discussion. I was just going to pass the baton to Jason and or Tatsu, I guess, and continue the discussion there if you have any questions for David.
Yeah, I
Thank
do.
you so much, David.
Oh, sorry. I had a question. No.
Okay.
David, do you give them a template, and is there enough room for them to do the work on one page?
That's the issue. A lot of problems, there's room to do it on one page. Sometimes you have to give them a couple. They can use the strategy, the template, but make it into a couple page document. Same thing is true with the formula fact sheet. On the really complicated problems, it might take more than one page. Same thing with the formula fact sheet. It's hard to use really tiny print on my formula fact sheet, for example. So you have to be really flexible with that.
And
but
this
they
is
pretty
done.
much tried to use the template in the beginning. It kept them kind of organized.
This is not done with the students. This is also when they take home the homework. They use the template. Is that right?
Yes.
When they take the homework. Yes. Okay,
Yeah.
Thank you.
Yeah.
So Dave, I had a question.
Yes.
I do pretty much the same thing as you do. I actually teach the 5 kinematics equations to my students. I do have a question. I usually tell them not to put units and when they are plugging numbers in the equations, because in my experience, many students confuse the units with variables, especially when you get to mass and meters and things like that. And I usually tell them to put the units at the end. What have you tried that? What do you think of that?
Well, I've done, let me share that one document again. Let's see if I can find it real quick. I would do a units check like this. And that's you may not need to leave the units out here as long as they're included in some kind of a units check. Where
Okay.
each term is listed. Let me see if I can find another one here.
Okay.
Yeah, here we got all the units added together, term by term. Make sure they keep the units proper all the way through. That'd be fine as long as
Yeah.
they do this units check. That would suffice.
And I have another quick question. How many problems would you go to like that, say in a 40-minute lesson?
Wow.
45-minute lesson, like, in a typical block.
Yeah, what I tried to do is in my teaching was take the first day or so and teach theory and sort of the demonstrations and talk about the ideas. Let me get into problem solving this sometime in the second day. I would probably try to do about maybe 3 problems,
Okay.
something
Yeah.
like that.
Yeah, 3 to 4, maybe you would
Yeah.
say with all the details.
And start
Okay.
them off with simpler ones, of course, and then build up.
Yeah.
Mhm.
Okay. Thank you very much.
Thank you.
I
Glad
think
you're
we
having
have a
success
hand
with it.
raised. Mukesh, go
Yeah,
ahead, please.
David. So I use pretty much the same strategy that you have described here. But one thing that I found with the students is that it's very hard to convince them to change their behavior. And I mean, how hard have you found it to change their what they are doing, how they do it, which is mostly writing it randomly in different places.
Randomly, right? No,
Right,
it's very
so-
hard. And so
So
like if
it's
you possibly
how
begin
long
to-
does it take for students to actually really become proficient in the method that you described?
I'd say a couple of weeks at least.
Couple of weeks?
In the beginning, they really kind of kicked at it. They said, why do you care how I get the answer? I said, well, because even in simple problems, it develops the strategy and the logic and the organization. So when you get to a more difficult problem, you'll know how to do it. But they would,
No, I mean,
that's why you got to require it. If you don't require it, they'll say, I'm just doing it my own way. I don't care.
right, because I do exactly the same thing, but even at the end of the semester, I have at least half the students who still keep doing what they were doing at the beginning of
Really?
the semester.
Even if you grade them accordingly, or? Because if my students don't draw a diagram, they get points taken off, even if they get the answer correct.
Well, I do the same thing. Well, I'm not as strict, probably. Maybe I should, that's what I should do. Take points off when they don't draw the diagrams.
I think if you don't do that, they'll just, I had the same experience. I fought the same battle as you've been fighting. If you don't make them do it, they will say, I don't care. I'm just doing it my way. Well, do it your way. You can have credit in the problem. You go ahead. So it wasn't that heartless.
Another great answer is to say, do you want to learn the physics or do you just want to get rid of the assignment?
Yeah, exactly.
I think their goal most of the time I see, they just want to get through. So we have to force them to make them learn. I think that's the whole idea.
But if you ask them, you put them in the position that they have to decide what they want to do. And if they really want to learn, okay, you want to learn, then you do it this way.
Yeah, well, many times you don't get any answer when you ask that question.
I agree with you. Because I go through the same hurdles, but that's my standard.
What I would do sometimes on the test is say, just draw the diagram for this one. Or draw the diagram, list the knowns and the unknowns.
I do ask them. In fact, I give them the structure just that you showed in some of the problems, especially when they have to do free body diagram and all those things. So I give them step by step. You do this, followed by this, followed by that. And they do follow through, but maybe I need to do a little bit more than just.
You're on the right track. I mean, just be patient.
David, there might be some questions in the chat we may not have answered yet. Let me see. Oops. There is one. Can you see the chat? Okay.
Yeah.
There is one from Jim.
Which one is that?
How could it be modified for more advanced problems later in the curriculum, like for undergraduate quantum mechanics?
Well, I found you can use it for, I never taught, I taught at the community college, never got past my freshman year, basically. But I can use it. It's really very, very effective in kinematics and dynamics and work in energy and so forth. I also did it in my electricity magnetism. It's helpful there too. I don't know about quantum mechanics. It's hard to draw a diagram there, but sketches help. I always draw a sketch too if I can. I see Carl ask about we have two principles like a ballistic pendulum. We have to do both. You have to do both conservation of linear momentum and conservation of energy. The two loop to loop where you have to do both conservation of mechanical energy and Newton's second law. Yeah, I mean, it might be said you do multiple approaches to that case. You might just divide it into two separate problems. The first problem is to find the velocity after the impact. And the second problem is to find the height that the ballistic pendulum goes up. Those are two separate problems, a kinematics work impulse momentum problem and a conservation of energy problem. Might just have two separate problems. Problem one is do this, problem two is do that. That's a possibility, sure.
I want to make sure David sees the comment from about 10 minutes ago from Becca.
Okay. What did it say?
Fun fact, Dr. Wright was my first ever physics professor, and he's still one of the best educators I've ever encountered.
Oh, thank you, Becca.
I thought that was wonderful.
But use your own style too. I mean, I tried using somebody else's program, verbatim, and I failed miserably. You got to make your own style come out and use stand upon the foundations that have been built by others, but make it your own. That's what I would say.
And then I think there's a question about sharing the presentation. I think all the presentations are going to be shared eventually.
All the presentations should be shared, right?
Yeah.
There'll be PowerPoint presentation. We should have the video of all the presentations too, hopefully.
Okay, I'm trying to see if we missed any questions or comments, but please say it if I'm not able to see it. Please unmute.
Well, a comment that I had was I thought your last thing that you were discussing, David, with Mukesh was particularly poignant. If we really feel that the most important thing is, are they drawing the diagrams right and are they understanding the reasoning? Do we even need to ask them to do the last step of construct numbers at the end for the actual problem? And should we be assigning more problems that are just asking them to do these first stages?
Now you've got a good point. Other than worrying about the only advantage, if you do a units check at the end, like one person mentioned, that keeps track of your algebra. Units don't work out right. You made an algebra mistake, for example. But even just plugging in the numbers, you don't get an idea to see whether the magnitude counts, but we ought to do that much more often. I agree with you. Just set it up, solve it symbolically, check your units, bingo. Who cares about the number? The process is what's important, not the final answer. You're very right.
Because it often can take them as much time to plug the numbers in as it takes them to do the rest of that stuff. And if we don't care that much about that aspect, should we really be asking them to do that as much? I mean, of course, getting numbers is important for some things. So it's not like, just wipe that out of the curriculum, but
right.
Is it so important that we have them do that for every problem?
Yeah, when I was in college, we had slide rules. So we didn't have a calculator. So we couldn't do as much of the adding the mathematics in. But yeah, I love that point. We should do a lot more of just the setting up. That's most of the problem. You set it up, you get the idea of what's happening, divide it up into pieces, you solve it symbolically. Who cares what happens after that, as long as your units check. Yeah, exactly.
But if
I would say, as David was saying, that sometimes they get answers which are like, velocity being 5 micrometer per second for a satellite,
right.
Or sometimes they get velocity which is more than the speed of light. So for that purpose, they need to plug in numbers, otherwise it will be impossible. Yeah. And I see that a lot, at least at a community college level, where the numbers come out to be so bizarre that unless they actually plug in the numbers, they would not realize that they'll get very wrong numbers because they didn't do the conversion properly.
Right.
Or they did not use
some problems they pursued at the very end.
Yeah, they are not using calculator properly because they try to punch in everything in one shot, and they make a lot of mistakes in putting the numbers in.
Oh, yeah, I don't disagree with that. Level. Yeah, but again, I don't disagree with that. I mean, numbers are important for many things, but it might not be that they need to be used all the time. And, if we really want to emphasize that it's the understanding that's important, that's what we should be evaluating, is whether or not they've gotten, that level of understanding. And it might be a better way of trying to get to that goal.
David, I saw Ryan raising his hand, but then maybe he gave up. Ryan, would you like to still ask your question?
Oh, I was just going to chime in, but people just say it. But I was going to say for me, I'm teaching a lot of students that are aiming for the MIT, they're pre-health, and then the numbers, getting the sense of the order of the magnitude and making sure they're checking that is super important for them. But for a physics major, a lot less so, right? So it depends on your audience, right?
Yeah, good point. Good point.
Fantastic. I love that how you quantified wisdom for us, David. 50% carelessness. Okay, that's.
Yeah, I had no idea, but most of it was just they just copied the question. They looked randomly in the mess they had set up, but they couldn't find what variable they were going for. Their diagram was wrong. Only 8% were like algebra and trig mistakes. Most of the mistakes were either conceptual, 46%, and careless mistakes was 40%. So just slowing them down solves half the problem.
Yeah. Exactly. Fantastic. So, I think, sorry, we are about to wrap, our discussion. Go ahead, please. Yes, Lillian.
No, you sure? So I was going to make a comment because I tried something different this year with COVID. I added some step. And when I get, for example, for the dynamics problems, like David, you were talking about the diagrams, I spent one full lesson in just showing them how to draw free body diagrams. And usually what I do is I'll give them a handout with like 20 problems. They go, we have to do all this. I said, no, pick 5 for me to do. And I let them pick which ones they want me to do. And I do all the ones they want. Then I said, the rest for you to do as homework. And so I spent one on free body diagrams. And the next day, I spent another one helping them figure out the normal force, because they think the normal force is also always the weight.
Right.
And they always think the normal force points out. And it's not true. So I put a different situation, like upside down, like pressing a book against the ceiling. And they would ask, draw this for me, because to them it's like, Greek. And that's what I would do. And I think it improved a lot of the results I had, even with virtual instruction. But I hadn't done it before. I would kind of just walk them through, but I systematically took 2 days just to do that.
I think you're right. That they get that diagram right. That's the problem. That studying,
and-
just drawing diagrams and giving them
Exactly.
practice with
And
that is critical.
here's the bonus of that. Now that you taught exactly how to do it, you can ask for it. Because I
Ironically-
showed you how. So
Ironically
now
enough,
it becomes legitimate, like it's not like she never showed us how. I showed you how. I can ask and I will score you on this.
ironically
And I
enough,
was
I think
thinking
that
so
comes
much,
back
Leah.
to what David said earlier, his advice for his students, which is that you need to slow down. So that's something we need to do when teaching this to them. All right, I think that takes us to the end of our session. Am I right with that, Muge?
Yep.